Okay, so welcome to the conference. I'm really honored to be giving the first talk of the day. Thank you very much to George and James and Sabah for having me. It looks like a pretty well-rounded agenda. You'll be hearing talks about big data, about analytics, about data modeling, ontologies, query languages, and so on. I wanted to start with something a little bit different, maybe a little bit thought-provoking. So the search for the universal data model. The format of the talk will be a little bit different as well. There'll be very few words. It'll be mostly visual. And I'll start. Is it clear? Okay, so we'll be building a graph as I talk. I'll start with myself. So I'm Josh. Like George said, I co-founded Apache Tinkerpop before it was Apache back in 2009. And I'm going to start drawing some edges in this graph. So I've had a long-standing interest in knowledge representation, in the way we structure information, both in the outside world and in our own minds and in perception. Just a couple more nodes about me. I like trees. I like airplanes. More to the point, I have a background in the semantic web. I did my PhD on a semantic web topic that I'll touch on at the very end of this talk. In circa 2006, 2007, I was building these strange little programming languages around the idea of mental models and associations, trying to make some of those things a little bit more formal and turn them into things that you can use for programming and for inference. And then I found out about the semantic web. I created a language called Ripple. And if you're familiar with Gremlin, Ripple will look kind of familiar. That's kind of where the Turing complete path language came from. So I gave a talk on Ripple, and I got an email from a guy named Marco. He was also working on RDF-based computing. He had a framework called Nino. And we got together and worked on a startup for a little while. And then we met these guys from Sweden who were building what they call the graph database. That was Neo4j, of course. And their data model, I don't even remember us calling it property graphs at the time, but it was a simplified graph data model that we really liked. We wrote an API to kind of generalize it, and that led to Gremlin. So Gremlin was based on property graphs, and it was kind of inspired by the other things that we'd done. So that's Tinkerpop, or at least the beginnings of Tinkerpop. For the last couple of years, I've worked for Uber. I'm in charge of a project at Uber called data standardization. So if you've heard anything from our CEO lately, Dara, Uber would like to position itself as kind of an operating system for daily life. And I think one of the most important prerequisites for that is for all of our systems to be integrated at the schema level. So data standardization develops common schemas, common vocabularies that can be used throughout all of our services and our data sets, and tries to tie all those data sets and services together. And part of that has to do with mappings between data models. So we use things like Avro and Thrift and Protobuf, relational schemas, and so on. I won't be talking about those very much in this talk because I want to focus on something a little more unusual, which is mental representations. But that's that. And we have some of those data sets. We have around 200,000 data sets at Uber. They all have metadata about them. Some of them flow into our knowledge graph that happens to use Tinkerpop, of course. And we developed a data model for data standardization called algebraic property graphs. I published a preprint of a paper a couple of weeks ago about APG with my co-author, Ryan Wisniewski. Ryan's a mathematician who specializes in databases and category theory. And that just kind of gives us everything that we really need in terms of a data model that can integrate everything we use at Uber and also plays well with property graphs. So it's a formalization of property graphs that plays well with enterprise data. At the same time, Marco is working on something called the multi-model abstract data type, or MMADT. That's not the MMADT logo, which is something I made up for the slides. But the idea of that is similar, but more on the compute side. So MMADT is the kind of takes a common model for computation and applies it to various data models: property graphs, RDF, key value stores, document databases, and so on. And we're working to bring these two things together for Tinkerpop 4. And there are other efforts in the space that I could mention, particularly RDF star, that is aimed at standardization and kind of reconciling the two popular graph data models. There will be a community update for GQL on October 9th, where you'll get to hear about those things, as well as MMADT and APG. And there's an Egyptologist because it's kind of cool, and you'll see that later in the slides. So what is the universal graph data model? Well, let's not define it so much. Let's just kind of describe it. What do we want to put in here? So this is our container for the universal data model. We want it to be formal, like RDF. So you can think of that as, would a mathematician want to work with this? We want it to be kind of developer friendly. So like Tinkerpop or Gremlin or property graphs. So is this something a developer would want to work with? And then we also want it to be intuitive, and that's something that's a little harder to talk about, but that I'll be trying to talk about in this presentation. So you want that to be something that a kindergartner can work with, a graph data model that is just immediately understandable by anyone. So if you look in the domain of user interfaces, some of the most effective technologies there have been something that a small child might have suggested, like multi-touch. Can I finger paint with this? I did all these slides on an iPad. It's a wonderful device. There was multi-touch way back in the 80s, but it took decades more to develop the technology to the point where we have something like an iPad. But now that we have it, it's something that an engineer and a preschooler can both appreciate. So we want our data models to be like that too. So let's start by just kind of comparing property graphs and RDF in terms of their intuitiveness. RDF has a lot going for it. Like I say, it has a formal specification. It uses this notion of identifiers as URIs, so you can put everything into a universal space. You can create linked data. You can think of an RDF graph as a set of statements. You can find the union or the intersection or the complement of statements. It's very easy to compose data sets together with RDF. So there's absolutely nothing wrong with RDF. It's a wonderful data model. But so given that that's the case, why are property graphs so popular? And I think it has a lot to do with intuitiveness. An anecdote from recently, someone from Uber's advanced technology division got in touch with me about a project for which they were using Amazon Neptune. They showed me their data model, they showed me what they were doing, and they said their biggest pain point was they didn't have a schema language. They love Gremlin, but they didn't have a schema language. I said, well, Neptune, has an RDF mode too. You tried that out? And they said yes. They'd studied up on RDF, but they really preferred property graphs. And these are not dumb people. ATG is where we send some of our best and brightest. So I thought I would take a stab at trying to explain what might be a little bit more intuitive about property graphs. And I'm going to make the claim that the way we think about graphs is similar to the way we visualize things. So we like to use our visual faculties for thinking about graphs. So let's look at it from a visual point of view. If you know about property graphs and you know about RDF, you can assign labels to these things I'm going to put in the screen. But otherwise, you can just kind of appreciate it visually. In property graphs, you have two kinds of things that you can connect. You have vertices and you have property values. In RDF, similarly, you have literal values, and then you have two different kinds of nodes. You have URIs, which have a name or an identifier, and you have blank nodes that don't. So in terms of edges, or in terms of arrows that you can use to connect things, you have these three. You have vertex properties, you have edges, and you have edge properties. In RDF, you have these kinds of things. So you can connect URIs. Basically, you can draw an edge or a statement from anything that's a URI or a blank node, not a literal, and these are the combinations that you have. So far, so good. In property graphs, you have the notion of an edge label. Every edge has a label. Here are two edges with different labels connecting the same nodes. In RDF, it starts to look a little more complicated because statements don't have types. They do have predicates, but predicates are nodes within the graph. So if I'm going to draw them like this, I need to draw the predicates as more nodes in the graph. Why? Because we can make more statements. We can use that predicate as the object of a statement, as the subject of a statement. Of course, we can reuse the predicate for other statements. You can do the same thing in property graphs, but we don't need to draw them as nodes because they're not part of the graph. The labels are not things that you can make statements about. So vertices, our nodes in the graph, also have labels. You can think of that green node, maybe that's a person node. Maybe those yellow nodes are places nodes, or whatever you want them to be. We have property values. Maybe that's like a long value up there, and the rectangle is a string. You get the point. In RDF, again, things start to look a little more complicated. Every vertex doesn't necessarily have one type. It could have 0 types. It could have 1 type. It could have any number of types, and those types are expressed using statements. So if you want to express that visually, then you need to draw it like this. So we have these two blank nodes have a type of place. This blank node has a type of person, and that type, you notice I had to use a letter for it because it's really special, the RDF type, a URI there. And of course, RDF type can be and is the subject and the object of other statements. Okay, now we come to edge properties, and this is where we kind of hit a wall with RDF because RDF just doesn't have edge properties. So you can't draw an arrow from an arrow in RDF. It's a statement-centric data model where you can't make statements about statements. And RDF star addresses this shortcoming, but we're just talking about RDF versus property graphs right now. But property graphs aren't perfect either. Let's back up to this. So we have these 3 kinds of arrows. And why these 3 kinds exactly? If you were to hand a marker to a kindergartner and say, draw me a graph, they might do something like this. They draw a node, okay, give it a color, very nice, another node, and then draw an edge. Okay, that's something that anyone can understand. And then maybe a property value. Okay, good, that's a vertex property. And then you can draw an arrow from an arrow there. That's an edge property. Moving on, okay, here's another property value, and then, so that doesn't quite work, right? That's a property on an edge property. That's what we would call an edge meta property, and there aren't really any graph databases that support that. So, nice idea, but not really allowed. So our kindergartner says, okay, and continues drawing nodes, and we get this thing, okay? An arrow coming out of a literal. Well, that just can't be. That's not something that's supported. And then, okay, well, you told me I can draw arrows from arrows, right? Well, here's an arrow from an arrow. That would be something like an edge outgoing from a property. Okay, Titan kind of supported those at one point, but that's not really generally supported. And then this, okay, here's an edge to another edge. Okay, beautiful picture, give daddy back the pens. You just can't do that. It's pretty, but it's not a graph. Well, I'm going to make the argument it should be a graph. Anything that you can think, and then anything that you can represent visually like this, where you're just connecting things with arrows, should be allowed. Even crazy things like a figure 8 edge, an edge that points from itself to itself. I can't think of any possible way this would be useful, but on a structural level, you should be able to support this. APG supports this. It's at the schema level that you define, what's allowed and what isn't allowed. So I think with property graphs, though, we're also moving into hypergraph territory, and I'd like to illustrate that. So here's an edge. Here's an edge property. You can either think of that as an arrow on an arrow, or you can think of it as a relationship between three things. Let's draw a little border around this to kind of highlight the asymmetry of it. Once we've done that, we can take away the arrows without loss of information. We know that this is, say, this is a person vertex, this is a place vertex, and that's a timestamp, maybe a date, which is kind of node-like. So Josh was in London on October 4th, 2019. And that becomes a hyper relationship, and we can create other instances of that relationship. So, and we can join them. So somebody else was in London at a different time. And then what else can you do with hyper relationships? You can compose them. They can be used as vertices in further relationships. So, for example, Josh was in London on October 2019 from a start time of midnight to a start time of midnight, and so on and so forth. So it's a relatively small step from property graphs to hypergraphs. And I'd like to illustrate a hypergraph data model not from an engineering point of view. I could go into our data models at Uber and tell you about the ways in which we use hyper relationships. We don't really use that term, but we have types, we have records, and they're basically hyper relationships. But from the point of view of how we think, let's create a container. We'll give it a shape. And let's say this is a relationship for things that fly. So let's make it kind of visual. A thing that flies needs to have wings. Make it a little more interesting and say it also needs some landing gear. So if you're going to fly, you need to be able to land. And we'll start putting things into this box. So a bird obviously fits into this category. It has wings. It has landing gear. Let's try another type of object, an airplane. Has a little bit of a different kind of wings. Has landing gear. We can kind of generalize. And just for the sake of argument, here's a third thing. An eVTOL aircraft has landing gear. The wings are kind of different. The rotors are like rotating wings. So we kind of have to generalize, but we just make a choice. We're going to put this thing in the flying things category. And here are the landing gear. Here are the wings. These are basically fields in a record type. So backing up a little bit, I can't think of a better way to illustrate how a kindergartner might think than to give you an example from kindergarten. So this is something that blew my mind in kindergarten. This is a felt apple on a felt apple tree. You pick it up, you put it on the floor, you put an apple on it. That gets boring pretty quickly, so maybe you move it to the side. That looks kind of lopsided, so you put another apple on the other side to balance it out. Do the same thing, move them across, balance them out, move them across, balance them out. And what was really amazing to me, I mean, we're adults, we know where this is going, but a kindergartner doesn't. What really blew my mind is that you get the same sequence of numbers every time. I talked to friends on Facebook, and they also could remember similar aha moments where they realized there are patterns in your head that can be used to kind of predict the future. That the world is kind of rule-based, and you can discover these rules. So what do the patterns look like? Well, maybe they look something like this. 1 times 2 is 2. Maybe you kind of arrange the 1 on the left and the 2 on the right, which is something we do a lot of, kind of spatializing concepts. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and if I remember correctly, 8 times 2 is 16. So you basically have edges, but then you can put them together to create recursive data types. So you have a sequence, and those are kind of special in, in human cognition and memory, memory for sequences. You get 1, 2, 4, 8, 16. So that's something we might want in our data model. But back to hyperrelationships. If you can remember the first time you tried to think about why you can't pick yourself up, like, I still can't do it, and I've stopped thinking about why I can't do it, but if you're a small child, you have to think about it, and you need an explanation. So in our mind's eye, how do we do this? Ask an adult, and they'll probably tell you either that it's a silly question, or they'll try to be clever and think about Newton's laws. But what you really do is has more to do with visualization. So imagine yourself standing on terra firma, and then you pick yourself up. What does that look like? Well, it basically has to look like this. You pick yourself up, and then you're just kind of hovering above the ground, and that's kind of cool. But is that possible? So you try to reconcile this with other things that you know. You can do other things with this visualization. You can make yourself small and far away. You can flip yourself upside down. But what you really need to do is try to put yourself in a category. So let's bring back that flying things category and put yourself inside it. So you need wings, you need landing gear, and you try to match these things up with your own body and find that, okay, you kind of have feet, yeah, but the rest of it doesn't quite work. So maybe let's compare, the floating kid with the other types of flying thing that we know. This is kind of like if the flying things category is a product type or a record type. It has a thing that flies, it has wings, and it has feet. And this is kind of like a co-product type or a union type. Things that fly, they're either birds or they're airplanes or they're Superman, or in this case, they're an eVTOL. So you do a little pattern matching. So do I have wings like a bird's wings and feet like a bird's feet? Well, not really. I can flap my hands, but they're not quite wings. So that doesn't quite work. Do I have wings like in airplanes? Well, I've already tried this. No matter how fast I run, it doesn't generate any lift, so no, that doesn't work either. I don't have rotors, so that doesn't work. And you can kind of think of this as a Gremlin search. You're traversing to these different possibilities, and then you're filtering. Or this is even more similar to functional pattern matching in a language like Haskell or Scala. And I really think that this is how we think a lot of the time. And there are other ways that we think, and we could really go into depth there, but it's a 25-minute talk, so let's keep moving. What can you do if you have a data model that kind of spans between graph database data models and mental representations? Can you treat the brain as a graph database? Can you write data into it? Can you get data back out? And to a certain extent, the answer is yes, but with some qualifications. First of all, the topic of mental representations is really contentious. There are a lot of theories. There's nothing that I could say up here that someone wouldn't disagree with. But I've given you a little bit of my take on mental representations, and at least visual representations and how they correspond with graphs. And there are ways of writing data into the mind as tuples, and I'll illustrate that. See if I can time this right. Okay, let's do that again. All right, the timing wasn't perfect, but you get the point. So you saw a red dot, you heard a noise, and you saw me up here on stage doing strange things. So if you were to hear or see any two of those stimuli at the same time again, you would automatically think of the third. you hear the bell, you see the dot, you're going to look around for Josh. Where's Josh, doing these strange things up here? Or you see me ringing a bell, and you hear the bell, you're going to look for the dot. So it's a kind of inference that you do to complete that pattern. And you can train the brain using that trick. There's a whole field called cross-modal correspondences. I had a nice conversation a couple days ago with a very prolific researcher at Oxford, Professor Charles Spence, about correspondences, and kind of ran through some scenarios that I explored in my PhD thesis. I'll just spend a minute talking about that. There was this idea of creating feedback loops between a person and a machine, where the person and the machine are both perceiving the same event at the same time. They see the same thing, but the machine has access to information that the human doesn't have, and the machine adds to the human's perception of the event with certain well-timed cues. And again, we could spend another hour talking about augmentation, but the basic idea is that if you just add the right information at the right time, you can augment the human's perception of the event in a way that bypasses bypasses conscious awareness. So you kind of trick the brain into perceiving things that it wouldn't ordinarily. If you do it fast enough, if you do it within other constraints, so the brain is very particular about the protocol that's used. There are very specific time windows that you need to hit. So it's kind of like building a real-time system. Anyway, I'd be happy to talk much more on that topic after the talk, but I think I'm probably just about out of time. So with that, I'll basically just stop talking and let you think about the graph that we've created. Again, check out algebraic property graphs, check out MMADT. And that's that. Again, thanks for having me. And I think we do have time for any questions that you might have.
Yeah,
right?
yeah. So this is the part where you get to ask questions. So.
Hi, Jos. I'm Ruben. Thanks for a great talk. I'm an RDF guy, so I found your comparison very enlightening. Like property graphs, RDF, kind of blew my mind. However, there's a reason for the complexity of RDF, or so we claim. Namely, that is, our graphs have a global meaning. There's semantics to them, whereas that's not the same with property graphs. So does that change the comparison in any way? Like, does it make sense to have the complexity in order to have this global meaning, or still not justified complexity-wise?
Absolutely, and I probably didn't make that point strongly enough that, yes, there are definitely things that we want from RDF. Like I say, RDF scores over property graphs in multiple ways. One of the ways is that very idea that there are context-independent identifiers for things. You have these URIs, you can automatically merge graphs, and you then automatically have statements about the same thing. You have a statement about a certain resource in graph A, you have statements about the same resource in graph B. When you merge them, you have a graph with two statements about the same resource. That's a terrific property of RDF that is not usually shared by property graphs. So you do want that global notion of identity. And we have that in algebraic property graphs. I believe Marco has something similar in MMADT. So yes, absolutely. That's kind of one of the things that we want to put in that bag of, the universal data model. We want it to have a simple, visual representation, like I illustrated, and that is compatible actually with global URIs.
Thanks.
Yeah, sure.
We have maybe time for one more question. Anyone?
Oh, by the way, there'll be a panel later today where we're going to be talking about property graphs versus RDF some more. So.
Right, so thank you very much. It was really thought-provoking. So I wanted to ask, now we have on top of RDF, I mean after RDF has been defined, there have been languages being defined like OWL, OWL2, all the profiles, because they were trying to tackle the problem of decidability. So within this framework, what happens, or do you care, do you need to care?
Well, yeah, I don't want to give you the impression that I'm promoting one particular framework. In Tinkerbot 4, for example, we're going to be using algebraic property graphs. We're going to be using MMADT. We're going to be trying to get the good stuff out of RDF as well. I lost my train of thought. Can you repeat the last thing you said? You got me excited
about decidability. So do we
yeah.
still need to, do we care? Is there a way to care, or are we like uncharted territory and we're probably trying to shoot ourselves in the feet?
Yeah, so I was trying to say, you know, I'm not promoting this over these other things, but in terms of this, in terms of algebraic property graphs, decidability is a strong point because it's basically just a system of algebraic data types. That's the same sort of system that you use in functional programming languages. There's a nice bridge between algebraic data types and the simply typed lambda calculus. So at the very least, the decidability properties here are very well understood. So that's definitely one thing that we want in that bag of goodies for the universal data model.
Thank you.
Okay, thank you, Josh, once again. And yeah. So with that, we're closing the first keynote and we're going to move on to our next speaker.